have 45 minutes together, and so we have a presentation of around 30 minutes, and then we have a Q&A in the back. So please keep your questions for the end. And now I'm super excited to hand over to Jakob, for talking about like rack systems and vector databases, what I, of course, as a PM don't know much about. So I'm very happy to learn, and I'm excited what you have to share with us.
Thank you very much. Cool. Thanks. Nice to see you. As you said, I'm going to talk a little bit about retrieval augmented generation and different retrieval methods that are out there right now. It's quite a hype topic, obviously. I hope maybe just a quick show of hands. Who has not, or who has used any like GPT, Gemini, anything? I just want to get wake you up a bit. Okay, any hand that is not up? Okay, perfect. Who's a developer out here? Okay, pretty good. Who has built anything with LLMs using the APIs, using the SDK, not just prompting something, but actually cool. Who has built something with a RAG with? Who has tried a different retrieval method than text embeddings? Okay, one person, nice. 2%, 3%. Okay, nice, because that's exactly what we're going to talk about today. So we've heard a lot about retrieval augmented generation. If most of you have already some experience, that's fantastic. So we don't have to dive deep into the super basics, but we're basically a lot of work that I'm doing at the moment with our customers is looking at different types of retrieval methods and essentially building hybrid type of RAG systems that don't just build on text embeddings, but they, for example, use knowledge graphs, or they use text to SQL, or they use text to query, and so on. So that's one thing that I would like to show you a little bit about today. And I'm going to start with a very brief demo. That's a super simple RAG demo that I usually like to show as a custom built RAG architecture based on Google Cloud. And what essentially happens here is that I have this super simple front end, and I have a knowledge base that I can ingest data into. It's fairly basic. I can just upload PDFs here. As you can see, I have a couple of PDFs about, I don't know, Angela Merkel and Nargis Mohammadi. That's usually the favorite one, my favorite one that I pull up. Who's the Nobel Peace Prize winner of last year. So what I can do now with basic text embedding RAG, I can go ahead and ask a question against this knowledge base, and the RAG system ideally is going to give me an answer based on the knowledge base and the knowledge base only. Okay, so it's not going to hallucinate anything into this answer. So, for example, if I type in which city has the most bridges, basic question that you can ask any LLM, any larger LLM, right? It will give you an answer. In this case, I can determine the answer, so that it's as expected because I don't have any info in the knowledge base on this. But if I ask for a specific fact that's represented in the knowledge base, for example, who on the Nobel Peace Prize 2023, which is last year, I should ideally see that my text embeddings especially match respectively, and this is matched with some information from the knowledge base. And this, you can try out a couple of things. For example, change the year. This year, the Nobel Peace Prize was not awarded yet. So let's see what we get in this case. Right. So this works fairly well, right? It works pretty much as expected. But what if I want to ask a different type of question? So what if I want to ask a question that doesn't just ask for a specific fact, just like this one, but it could, for example, I might want to know who are the most, how are the most recent Nobel Prize winners. And this is super relevant because I mentioned this is a company knowledge base or some knowledge base of an organization, right? And we want our users to actually work with this and ask questions around legal topics or around any finance topic or any topic that you can imagine, right? sometimes they ask for specific facts that assumes that they already know what they're asking for. But sometimes it's going to be more a question like this, right? Which are the facts? Like, what are the most recent things that happened, or what is more of it's more of an abstractive question, right? They don't really know what they're searching for yet. And we want this information obviously to be represented real time, right? This is supposed to be up to date. And this is a bit more tricky. So if I type this question into this standard RAG using text embedding, and this, obviously, there's information on this represented in my knowledge base, right? But most text embedding systems are going to struggle with it. And I know if you tweak it a little bit here and there, probably you can make this question work. But on a general level, we have two different types of questions, right? One is a rather local question, what I call local questions, right? Asking for a specific extractive fact. And one is a rather global question. So this is a question that probably I'll need multiple documents to answer this. There's not just one document that contains this fact. But I need an abstractive knowledge around my knowledge base to actually answer this question. And for this, I have the second demo open here. And it's a bit more raw, but essentially the same concept, same documents in there mostly. And if I ask this here, this takes a little bit longer, but hopefully we actually get a meaningful answer. Right? And the major difference here is that it's the retrieval method that's behind that. So it's essentially a different method that we are feeding. We're looking at the query, we're looking at our database, and we're matching the information that's contained, or that the query is looking for, and and our knowledge base contains. And we're having a different method of actually matching these two things. See if you have the result, and we're still processing. And what's behind that is knowledge graphs. Knowledge graphs. Who has heard of graphs, or are you aware of graphs in general? More or less. Cool. So graphs are essentially a structure in mathematics. Right, it's pretty cool, right? We have basically most recent. It's actually the most recent in the knowledge base. We can tweak it a little bit. Maybe if you ask, give me a list of the Nobel Prize winners, we'll get some more. But we get an answer on this, right? This is pretty cool. So graphs are mathematical structures, networks, essentially, that you can use to represent all sorts of facts and knowledge and different things. You can represent social networks, you can represent knowledge, and they are super, super useful to really model things that have relationships. So they're consisting from nodes and edges. So you define essentially topics and specific facts. You define them as nodes. So these are essentially the bubbles here, and you can define relationships between these nodes, which are edges, and these nodes can have different descriptions and different types, and my edges can also have descriptions and types. So it's a very complex data format, but it's extremely useful to model knowledge. Also a little bit tough to work with, to be fair. And yeah, in the next 20-30 minutes, we're going to look at how this could work and how you could bring this into production in your company, in your organization as well. Here's the direct comparison again. On the one hand, we saw text embedding RAG, and on the other hand, we see graph RAG. Very brief architecture overview to dive deeper into it in the beginning. Just as a recap, text embedding RAG, we have a document, we split that into chunks. And you probably have seen this, right? You send that to an embedding model. You get the embeddings that represent the knowledge that you actually want to represent in your knowledge base. And once you use a query, query time comes in, you feed that in your embedding model again. You get a representation, a semantic representation of your query. You match that to all the embeddings in your embedding knowledge base. And the most similar ones essentially are your context for the final answer that you send to Gemini in this case. Pretty simple, pretty efficient. Works very well for exactly these specific facts that are already represented as a fact in your knowledge base. But we just saw if it's more aggregated, right? If we need to factor in multiple documents, for example, sometimes these text embeddings can really struggle to find the right knowledge, especially if it's not specifically mentioned. So in this case, graph can come in. Work completely differently. In the end, it comes back to a very different result. In the end, we have documents as an input as well. We then use Gemini or an LLM of your choice to look at all these documents, and we have a prompt set up that essentially instructs the LLM to extract my nodes and edges. So it basically asks, what are the main concepts? What are the nodes? Given you want to feed that in and annotate that as a knowledge graph. Right? What are the nodes? What are the edges? and we feed that into a graph database in this case. I'm going to talk about graph databases in a second as well, but let's just assume we have some way of storing this knowledge graph now, right? That makes it easily accessible. The second thing would be we need to actually understand what's in our knowledge graph. The knowledge graph is a bit of a complex, very vivid structure as well. So the second step would be we run a community detection algorithm over our knowledge graph. So that means it assumes that communities in our graph, so community would be groups of nodes that are more densely connected than they are to other nodes. So you might have 10 nodes here that are very densely connected with each other. You might 10 nodes up here. The groups might be connected, but they might just have one or two connections. But the groups in itself, they are very densely connected. So these are the communities, and these are the communities we want to find, because we assume that a community that's very densely connected in the knowledge graph is sort of a topic, that's these nodes are about. That's the assumption. So we run a community detection algorithm. That's actually a deterministic algorithm that we run. So we have this list of nodes that are mapped in communities. Then once the user query at query time comes in, we basically ask that user query with context of every single of these community reports. I forgot that part. So in the community, we basically generated report using Gemini as well, right? So we look at the community, what really connects it, what is the community about, what are the major facts and findings. And then we use these community reports as context for the incoming query. So we essentially, in the really raw format, and we can discuss about the efficiency of this later, but in the really raw form, we take a query coming in from the user, and we ask that with context of every single community report. So if we have 10 community reports, we have 10 queries that we ask to Gemini, user query plus community report, every single match, right? And we check, okay, what's the intermediate answer for this, and how relevant was really this community for the user query. You'll get some scores there. Then in the end, you take the most relevant communities to answer this specific user query, and these are essentially then the context for our final answer. And that's pretty much the pipeline you have for GraphRag. Result is, again, on the one hand, text embeddings. They're very good for extracting content and specific facts, and they're very, very quick and very efficient for doing that. GraphRag is a little bit more overhead, actually quite a bit more overhead, but it allows you to really ask these aggregated questions, right? That's the really, really sweet part about this. And I'm going to go a little bit into this about knowledge graphs. Obviously, in GraphRag, it's quite a hot topic at the moment. If you want to dive deeper into it, GraphRag, what kicked off the discussion about GraphRag is the Microsoft open source project about GraphRag. Maybe you've seen it. Take a look. They have a good publication around this. I'm going to show you my implementation of this in a second as well, obviously. But this is a good starting point. If you want to get started into the topic, then the Microsoft implementation might be a good place to start. The developers of the EU might be able to relate with something like this. The next 28 minutes are going to be basically about how I implemented the GraphRag topic myself, a little bit of the ups and downs and the learnings that I took, the best practices, sort of the major decision points that you might go through if you decide implementing GraphRag from scratch, or also based on an open source project, right? But there are a lot of sort of corner points that I'd like to discuss. So first point, when talking about knowledge graphs and annotating knowledge using knowledge graphs is how to actually make sure that your annotation is right, because it's the LLM prompt is essentially such a probabilistic situation. So how to make sure that actually all the data that you need is represented in your graph. If you just send an LLM prompt and basically tell the LLM, okay, just extract me all the nodes and edges, right? But the difficult part about knowledge graphs is, and already traditionally, they're quite, theoretically, they're amazing, but they're very difficult to work with due to a couple of reasons. For example, one reason is the ambiguity of relevance, right? Imagine, so Google is also built on a knowledge graph largely, right? So if you Google Warren Buffett, you'll not just get the results, but you'll get this little bar that states some facts, his age, spouse, and some other facts, right? this is based on Google's knowledge graph because it connects different pieces of knowledge that might be relevant for your search in this case, right? This knowledge graph is the biggest knowledge graph in the world, actually, maintained by Google Search, so it's pretty impressive. But they make very clear decisions about what's relevant. I think they have 3 or 4 different types of nodes that they include in this knowledge graph only, right? It's, I think, person, place, event, and something else, something like that, right? So it's a very limited space of nodes types that they actually include. This is a super crucial discussion because imagine you have a knowledge, piece of knowledge graph about Warren Buffett, right? What do you include and exclude? If you look at all the information you have about Warren Buffett, you could include, okay, philanthropist, investor. You could make connections to all the companies. You could also include the color of his tie at the last board meeting, right? You could include any piece of information. That makes it so powerful, but that also makes it so difficult to work with, right? So you need to have a relevance cutoff. Where do you stop including knowledge into your knowledge graph? Seems more trivial than it actually is. It's actually really tough discussion, right? So where to make this relevance cutoff. So this will be a major discussion if you really look at the knowledge graph for your own knowledge base. This will be a major discussion. Really, in the practice of writing this prompt, you'll have to think about which entity types and node types are you going to look at. Is it going to be people and places and concepts, or are you going to add events? Depending on your use case, depending on the data you're going to include in this knowledge base, this is going to look extremely different, right? So given those, where's the relevance cutoff, right? Well, how do you decide which knowledge is in the knowledge graph or should be in there and which not? And finally, how to make sure that these extraction results are actually complete, right? Even after you decided what's the relevance cutoff, how to really make sure, and how to also test, right? How to also test once you extract it, that actually all the information is in there. Super, super tough. Right, going a little bit into this, actually I realized, okay, at least on a basic level, this is not so hard, right? This is a little bit of my prompt that I used. Essentially, it's giving a goal, it's giving some steps, entity name, entity types, then it's feeding the entire thing into a semi-structured format. I don't know if you can really read this, probably not, but I think the concept is more or less clear. You very clearly define what are the entity types that's here. We have an input variable for the specific entity types that you're looking for. You give a structured format that this should be, poured into, and you define how the edges are going to be defined, source entity, target entity. You ask for relationship description for these edges, and you ask for a relationship strength. So how strong is essentially the connection, how relevant is it, right? And you can really, in practice, fiddle around with this prompt as much as you can. That's not the one answer here. Again, a lot of ambiguity in this extraction step. Nevertheless, I would say keep it simple and specific for your use case, right? Think about what are the questions that users are going to ask, what knowledge needs to be included in your knowledge base, and then really feed that into a prompt similar to this one. Ideally, also match it with sort of a function calling that you can feed it into structured output directly. I also used multi-shot examples. That really pushed it over the finish line quite a bit, especially if you want structured output. And I mean, all of this is sort of semi-structured. So multi-shot examples are super, super crucial. So that basically means, if you check out the repo, you can check out the full prompt. That's the link to the GitHub and the QR code. But there are essentially examples of inputs and outputs. So examples of, this is a piece of text, these are the entity types. And given that, these are the nodes and edges that I would want to extract from this piece of text, right? I have like 5 or 8 or something like that. So multi-shot examples really push this over the edge. And this is working quite decently. Another point here, I actually prompt the model multiple times. I use a multi-turn model in this case, and I actually let the model improve itself. So I give this prompt one time, and I take the results. And then, given all the history and this initial prompt, I ask, okay, extract more nodes and edges, improve yourself, right? I do that, I think, 2 or 3 times. You can do it arbitrarily much, but obviously the cost also increases as much as you prompt. So that's the extraction piece. Cool, we have the graph extracted. We have nodes and edges. We have that super complete, fantastic. Now, whoever worked with knowledge graphs before, or graphs in general before, probably looked at some of these tools to also store them. Graphs are fun to work with as long as you can store everything in memory. Once you have to start working with graph databases, usually it becomes very painful because you add a completely new database to your tech stack. They have a new query language. They run on Cypher. It's there's no looking at these. There's no really decent serverless option as well. I'm a big serverless fan. I want to have minimal setup effort. There's not really an option. All of these are kind of, you have to make big setbacks of some sense. So I decided essentially knowledge graphs are just a unstructured data form, or semi-structured data form in the right data model. So with the right data model, you can actually just use any NoSQL database to store your knowledge graph, right? That's what I did in this case. I didn't want to deal with the extra tech debt sort of included in my architecture. So I'm a big, as I said, I love serverless. So I'm a big Firestore fan. So I used Firestore to actually store my knowledge graph. If you define a good data model around this, and you define some basic interactions that you need to do with your knowledge graph. So I also published this graph to NoSQL. Essentially, that just gives you this data model, defines how edge data is supposed to look like, defines node data, defines community data. These are essentially the big three data types. Then I separate collections within Firestore for nodes and for edges, right? And I make sure that, for example, if I add so in my operations, in the interactions, right, in the Python interface, if I add an edge, that needs to be also added as reference in my nodes, right? So make sure that all these operations are sort of taken care of. And that works extremely well and extremely lean. So I can just recommend to you, if graph databases are what's stopping you to get into knowledge graphs, then just go for some setup like this. It works incredibly well, actually. You choose the right NoSQL interface. All good. We can do questions afterwards. Right, next step. So you have this stored in your Firestore. Fantastic. You can interact with it very easily. Now, what to do about graph understanding? That's the next steps. I mentioned these communities. So there are a lot of decisions to make here. There are lots of community detection algorithms out there. You can really deep dive into graph theory on how to do this best. There's things like graph embeddings, also very interesting topics that don't take text, but they take graphs and their nodes and edges, and they embed each of these, right? And how to write the community prompt as a community reporting prompt as well. And all these are things you will have to think about. In the community detection, again, you can dive deeper into the theory, what's relevant for you in this case. In my case, I just went with Lorraine communities. It's fairly standard community detection algorithm. Uses random walks to decide which communities I should define. That works very well. It's well integrated. It has Python libraries and so on. So yeah, my advice would be go with the easiest and the simplest option that works for your case, and then get more complex and get into the theory once you need it, right? Secondly, node-to-vec embedding, super interesting topic. Would be really useful going forward if you want to, I don't know, do edge prediction, so predict edges that you don't even have represented in your text or that your LLM missed at extraction time. Super interesting topic. I haven't explored it myself yet, but yeah, my advice here would be keep it to the side for the sake of time, basically. But once you have time, definitely look into this node-to-vec. I think it has massive potential to make your knowledge graph more complete, essentially. And then the community reporting prompt, again, there's not this one right option, right? There's not this one solution, essentially. In the end, you'll look at the communities, you'll feed that information into your LLM prompt, and you need some sort of informative report about the community, what it's about, which nodes are included, and what an LLM should know if a question is asked that this community might be helpful to answer, right? My prompt looks something like this. It's not very readable, but I can give you, essentially it's just asking, write a comprehensive report of a community, giving a list of entities that belong to a community, as well as their relationships. Then it sets the structure. So there's a title, there's a summary, there's an impact severity rating, how impactful is this community for the wider knowledge graph, an explanation of this rating, and the detailed findings. The detailed findings are interesting because usually have you see one single data point also here on the right. You have this the summary, right? That's like, okay, what's going on in this community, and then you have detailed findings. So detailed findings are just interesting additional facts. It's not really closely defined, but interesting facts that are also relevant about this community. Right? I know it's a little bit ambiguous, but maybe if you try it out, you'll get a bit more feel. But for example, this community report, it's concluding Robert F. Kennedy Jr., U.S. Senate, the U.S. House, the 2024 United States presidential election, and the U.S. Electoral College. It's the community name is 2024 presidential election and Robert F. Kennedy. So Robert F. Kennedy is one of the independent candidates. I don't know if you're following the election there a little bit, or was. And then the findings are something like, okay, the 2024 US presidential election is a pivotal event, and then some details about this. And Robert F. Kennedy is the decision to run as an independent candidate, yada, yada. So it's like more specific facts that is also interesting about the community that might, be relevant just looking at the connections and notes. Yeah, this is actually working extremely well. You have function calling connected there as well, so you get a structured output that gives you exactly this data structure. I showed you how the data structure looks like before as well. So there's community data, community notes, the summary, the document ID, where it's from, and some others, right? And this can be easily fed into your graph to NoSQL, for example. Right, so it was not so bad at all. Finally, so now we're at the step that we have these community reports in our NoSQL database, right? And now it's essentially the ingestion is done, and we do need to query this entire thing. To query this entire thing, we'll use a MapReduce logic that essentially frames the notion of asking a community report, or every single community report that you have stored, that question that the user also asks, and then having this intermediate query and rating the intermediate query, that it frames it as sort of a function with static input, or a stateless function, right? That is the map step. So essentially spread this out. The map step is we take every single community report that's stored, we feed that into an LLM with the user query, and we get an intermediate answer and a relevance score. Right? How relevant was this community report to answering this user query? That's the map step. So that's essentially spread out. And the reduce step, also it's a bit small on the slide, but the reduce step essentially then takes these intermediate queries, looks at which intermediate queries scored the best. Right? Most of the time, it's very sparse in the sense that just a few communities score very well, and most of them score 0. Right? Makes sense, I guess. So we take the top N communities and we feed these communities in our final LLM prompt. That's the reduce step, right? And that's the final response we get. You could also think about not just using the community report, but using all the node information about the nodes in those communities and edge information. That's sort of arbitrary in how you want to solve this. But yeah, this is actually fairly straightforward. Once you have this entire community ingestion, community reporting done, this is actually a very straightforward piece. So yeah, the only thing to think about, and we're going to come to that later, is really the latency and the cost of all of this, because you're doing a lot of LLM calls, especially at scale, right? If you have a lot of communities, that becomes very expensive. But I have a couple of ideas on this in a second. Right, that's the overview again. Essentially, we spread, like every RAG system, we spread an ingestion in the extraction layer. Ingestion layer takes a PDF or any unstructured document. OCRs that, in my case, the document EI. Obviously, I'm building Google Cloud Native, so document EI for OCR. Then I have Gemini doing the node and edge extraction. I feed that into my Firestore with graph to NoSQL. Then at step 3, I run the community detection, and I take these communities and feed them again to Gemini to generate this community report. That is also stored in Firestore alongside with my graph data. And then extraction layer would be query time, client query coming in. At step 4, you have first this map step, right? Intermediate answer is, or every community report is matched with the client query, producing an intermediate answer and relevance score. And we do step by ordering these relevance scores and using the most relevant communities and nodes respectively to generate a final response. Right? Yeah, that's pretty much the result. That's exactly the architecture that I just showed you in the beginning. Now, for the a little bit attentive ones among you that thought about the latency and of all of this, it might be obvious that this can become very expensive at scale because you're doing a lot of LLM calls, especially at the ingestion time for the community reports, and secondly at query time for intermediate query generation, right? Essentially, you're scanning, because in theory, for every single document uploaded, it might be that a new document adds just one single node to every community in the worst case. So you have to regenerate every single community report. At query time, in the standard mode, you will have to run a single LLM prompt with every single community report in your knowledge base. Right? So this is much less than scanning all your documents, but it's still very expensive scale. Obviously, models are getting smaller, models are getting cheaper, but nevertheless, it's a massive latency issue and also cost issue. The latency issue is fairly easily solvable, basically through this architecture. Looks a bit overwhelming, but essentially it's exactly the same that I just showed you on the previous slide. The only thing that's happening is that these two steps, community report generation and intermediate answer generation, these are essentially the parallelizable steps. So these are steps that I can define as a stateless microservice, and I can just outsource that and parallelize, right? So I have pops up as a messaging queue that the front end essentially once the document is uploaded, and I have the communities for community report generation. I know, okay, these are the communities that need to be generated. I just from the front end, from the client, I send a pops up message to my pops up queue that then has a stateless worker connected to it that does the work in parallel. So I at least don't have the latency of concurrent processing here. Same happens for query time as well. At query time, basically, I send a tuple of query, user query, and community port every tuple to the PubSub query, PubSub queue that parallelizes in terms of the processing. So essentially, from concurrent processing, I reduce down to just the latency of one single prompt. That works extremely well. Still doesn't fully solve the cost issue, because you have the same amount of tokens you feed in, but the only latency is reduced. Ideas to solve this are obviously filtering which knowledge you have to regenerate. So you'll never get to the same cost proposition that you have with text embedding rack. I can promise you that. You just need more LLM calls, but you also have an inherent additional value that comes out of that you can answer more abstractive questions, right? So these abstractive answers come at quite a price. To improve the pricing point, you could think, for example, about filtering very detailed which communities you need to regenerate. So before you send to regeneration, you have to make sure that you only regenerate the communities that have actually changed, but that's actually fairly straightforward. Then you improve that already quite a bit. The query generation, the intermediate response generation is a bit more tricky actually, because you need to have some sort of filter that predicts the relevance score before you look at the community port and the query match. It's a bit more of a tricky problem. You could try to do that by text embeddings, for example, try to get like an approximation. I don't have the final solution for this yet. If you have any ideas, feel free to let me know. But that's essentially this step here is the super crucial part that is really the make and break, gonna be the make and break in terms of costs. What's gonna make it worth it? How do you decide whether a community port is relevant for the question, right? If you use embeddings, then you have the issue of, okay, maybe you have this extractive, less of this abstractive knowledge again. So it's really a chicken egg problem in this case. Right. thinking about this, so thinking about this becoming more expensive. Let me finish with this one. So just as a summary, you have resources here. Also recently published a blog about this, and you'll find the GitHub implementation on the right there, and you'll find Mind Socials there. Just sort of summing up the entire topic. What are the major decision points that you want to look at? First of all, you'll need to think about this tech stack, where do you store the graph? This is a super pivotal decision. Make sure you think about this well. Do you want to include a graph database or not? Graph native database or not? Very, very important one. Secondly, is going to be the cost, right? Think about the cost, how to reduce it, and whether it's worth it to include this abstractive question at the cost point that it comes with. Third point, latency. We saw some orchestration options, right? If you really orchestrate it as a multi-service microservice architecture, latency-wise, you can reduce it a lot. That's actually pretty okay. But still is an important one to think about, because there's more architecture pieces than with your text embedding rack. And finally, the prompting. The prompting is going to be a never-ending optimization, a never-ending iteration. Also, it might make sense to really fine-tune one of your LLMs to do this extraction and do this intermediate response generation. So yeah, that's going to be a never-ending process. Optimize the prompt for your specific use case, and then if you have the data, fine-tune it. But for sure, use multi-shot examples. That would be my advice on this. And maybe just a couple last thoughts and maybe discussion points for the one afterwards as well. I believe that RAG, just like so many other design practices, will go into the hybrid direction. So not everything is going to look like that. It's going to be way too expensive. Not everything is going to be on only text embeddings. It's going to be way too less performant. Probably you'll have some hybrid setup that has an orchestration layer that once a query comes in, decides which of the two or more retrieval methods you need, right? Because think, for example, about even other questions that might be asked, right? What if there are very quantitative questions for specific statistics? These will be fine, but they won't perform very well because both of these don't really work well with numbers. They don't have a deterministic source for numbers. They can aggregate numbers very well. Right, so there might be a third option that you have with text to SQL, or there's another method that I actually yesterday read about, published by Google as well. That's called RIG, retrieval into lead generation. That essentially, in the process of generating an answer, generates queries for statistics that you're missing. So very, very interesting topic to look at as well. Overall, I believe hybrid is the way to go. Orchestration layer, sort of intent detection, which of the one is it going to be, and then you essentially route the query to the right pillar. That's about it.
Thank you so much. Before you're leaving, we have a little bit time for 1 to 2 questions for Jakob. Thank you so much, also from my side. And yeah, so feel free to shoot, and yeah, handing over. So it's ready. You can
okay, very well.
Yeah.
Hi, I have a question. So as far as I understand, the general RAG stack is you upload documents. Out of documents, you generate like chunks of text.
Yeah.
Right, and then when a query comes in, you figure out which chunks of text are similar to the query, and then use them for generation, basically. Right. So I think in the text embedding, the chunks generation is trivial. You just take pages, right? And then the text, paragraphs of documents. Then the similarity is essentially text embeddings based similarity to find the important chunks, and then you generate the answer. So in the graph RAG, the chunk extraction is, you use your graph algorithm to come up with the community reports. Those are your chunks. And then the similarities, like figuring out which chunks are relevant to the query, you use using an LLM. So I think that this is, maybe not necessarily comparing apples to apples, because in the similarity in the RAG, you use a very simple method using text embedding based similarity. In the graph RAG, the similarity is LLM-based similarity. And this design trust is kind of orthogonal to the whole graph business. As you said, for the graph embedding, for the graph RAG, you can also use embedding-based similarity of community reports. And in the same way, you can use LLM-based similarity with the text embedding RAG.
Yeah.
And so I was wondering if you've run an apples to apples comparison when you've used either the graph RAG with text embeddings based similarity, or the simple RAG with LLM based similarity, to kind of marginalize over that design choice and really look at what is the impact of graph on the quality of answers.
How would LLM-based similarity look like in the left case?
Right, so you chunk your documents, and then you come in a query every chunk. You ask Gemini, well, is this chunk relevant to the query? And do this. That's the same mechanism used when you combine a community report with the question, right? You get, oh, is this community report relevant to the question? Give me an answer for that question from the community report. It's community answer business. You can do that by feeding it the chunk of documents, not the community report. And but I guess what I'm going for is my hypothesis is that if you ask what are the top Nobel laureates, so this overarching question, and if you ask that question to every chunk, it will just extract Nobel laureates from every chunk. You will have a summary of all the Nobel laureates in your database, and you can also answer this question. And you wouldn't need to deal with the graph business all together. That's why I'm asking.
Fair enough. But
I'm not saying that this is the case, but it could be the case, and I'm very interested to see if that really would be the case.
No, I see your point. The issue with that, underline you're right. Probably this would work well, because this is exactly what you're doing on the right side. You're essentially asking more or less all the chunks that all the abstraction chunks that you could create, right? The issue with that is that RAG essentially tries to enable you that you don't have to scan your entire database for every query, right? Because that's going to be extremely expensive. For 20 documents, just like here, that's going to be fine. But if you have 1 million or 10 million documents, you have to, for just one question, you have to scan, millions, billions of tokens for just one single question. That will probably perform the best, I agree, but it's going to be insanely expensive.
So if I understand right, you're saying that the graph is used to essentially compress your document database into a more manageable size. Okay, fair enough. Maybe so. It's like a summarization algorithm that's used for document preprocessing.
In some sense, you could understand.
So okay, you see what I'm going. Have you tried other summarization algorithms? I'm just saying, I think it's a very valuable proposition. We're trying to distill the impact of the graph on the whole stack, because it seems like there are very many design choices. And
100%.
But maybe I don't know.
Maybe
all of the time,
but I agree. One approach is, for example, just taking embedding summarizations as well, right? That's definitely an approach. So not just embedding the chunks on the left, not just taking the raw chunks, but looking at chunks, like summarize 3 chunks and then embed that. Yeah, for sure. Or you could take the graph or whatever structure and then you feed that into your embedding, for sure. I've tried it myself. I've seen studies on it as well, so it's definitely
so I understand that this is a demo, not like a kind of ablation study of this sort. That's not the case. I'm just interested to see if you maybe have or done a thorough ablation study of this stack to see the impact of individual changes. But if you do, I would be super happy to read it offline.
For sure. We'll follow up on this. I haven't so far, but it's definitely something. Super valid point you made.